Greetings. We will continue our discussion on the variational principle. We started out in the previous lecture, we showed that this is an alternative way of accounting for how objects move and how their equilibrium changes. Equilibrium does not change as long as its motion is determined completely by inertia and by initial conditions alone. And then when it changes, Newton's mechanics accounts for it by invoking the cause effect relationship, that there is a stimulus which induces the system to change its equilibrium. It forces the system to change its equilibrium at a rate which is dp by dt, that is the rate at which the momentum changes. And the variational principle accounts for it in a completely different way without referring to the idea of force at all. And this is really remarkable, that Newtonian mechanics makes no reference to a variational principle and the variational principle makes no reference to force, but both are able to account for the mechanical motion, equilibrium and its departure from equilibrium in their own way. So, the variational principle relies on this, that this integral which is called as action, it this is the functional, it depends on the Lagrangian, which in turn depends on the position and velocity q and q dot, and this action must be an extremum, which means that it should be stationary. Okay. It is often called as the principle of least action, but the term least can be misleading, although it is quite appropriate in most situations. It is correctly described as the principle of extremum action. It is a stationary action, is stationary. It means that it is optimized, but it could be least, it could be a minimum, it can even be a maximum, it can even be a saddle point. So, stationarity is much more general an idea than having a minimum, and this principle refers to the principle of extremum action. And what this principle tells us, it describes the mechanical motion of objects. It does not explain it, it describes it. There is a difference between explaining why things happen the way they do and describing what is the correct law which describes the motion. So, this is an accurate quantitative description of the law, okay, which is why it is called as a law, because it gives an accurate description and it describes how motion takes place. And its contention is, the statement of this principle is that motion takes place in such a way that this definite integral, which is called as action, it is the integral of the Lagrangian between the start of the event and the finish of the event between t1 and t2, that this integral must be an extremum. So, we determine what this Lagrangian would be like, and it is a function of speed, function of velocity and position, which is the obvious choice. And since space is isotropic, the right kind of function to be selected, which is the function of velocity, would have a quadratic form, because then it becomes independent of the direction. So, you have f1 q dot square plus f2 q. So, which can suggest to you that these must be the kinetic energy and the potential energy, because the kinetic energy depends on the square of the velocity and the potential energy depends on the position itself. And we found that the condition for this action to be an extremum is that this equation, which is a partial derivative, which involves partial derivative of the Lagrangian with respect to position and velocity, and subsequently the time derivative of del L by del Q dot, that this equation is satisfied. And we choose the Lagrangian to be t minus v. This is a good choice. This is the right choice because it gives you an immediate correspondence with Newtonian mechanics. Because when you take the partial derivative with respect to q, you get the rate of change of momentum, which is also what you get when you take the time derivative of the partial derivative of the Lagrangian with respect to the velocity, which is now appropriately called as the generalized velocity. The q dot is the generalized velocity, and the partial derivative of Lagrangian with respect to q dot is the generalized momentum. So, we will use the more formal vocabulary of generalized coordinates, generalized velocity and generalized momentum in this formalism. And we can carry out the transformations from position velocity to position and momentum because they are completely equivalent, and once you carry out these transformations, you can describe the system in terms of qp instead of q dot. And when you do that, you recognize that when the Lagrangian is independent of some coordinate, this may well happen under certain situations depending on what kind of symmetry properties the space has. And depending on that, if the Lagrangian is independent of some coordinate, then from the Lagrange equation we immediately see that the time derivative of the generalized momentum goes to 0, which means that the generalized momentum would be conserved, and you will immediately be able to connect it to the principle which connected symmetry with conservation laws, which is very nicely formulated in Noether's theorem, that there is a symmetry because the Lagrangian is independent of the coordinates. So, there is a symmetry which is implied, and the corresponding canonically conjugate momentum is conserved. It does not change with time. So, it is a constant of motion. So, just consider in an inertial frame of reference, if you are in a homogeneous space, then if you have a Lagrangian, then because space is homogeneous, a change in the Lagrangian, if you change the coordinate x coordinate by delta x, y by delta y and z by delta z, will leave the Lagrangian invariant because of the symmetry. And if this is to happen for arbitrary displacements delta x, delta y and delta z, then it means that the coefficients of these displacements, which are the partial derivatives, which are individually 0. So, del L by del x must be 0 and del L by del y should be equal to 0. So, this is the statement which connects the symmetry and conservation laws, okay? So, which is the content of Noether's theorem. So, if you write the Lagrangian in a more general way by including dependence on time, then the derivative of the Lagrangian will be because of the Lagrangian depends on the position and the position depends on time. The Lagrangian also depends on the velocity, but the velocity itself depends on time. So, it has got a second derivative. And in addition to that, the Lagrangian may have an explicit dependence on time, which is the partial derivative of Lagrangian with respect to time. So, if you use the Lagrange's equation to describe del L by del Q as d by dt of the generalized momentum, then you immediately see that you can combine these terms and write this term and this term. These are both total derivatives. So, one minus the other is equal to this term, which is moved to the other side of the equation. So, there is a minus sign here, and it obviously tells you that when the Lagrangian is dependent on time, this is the expression that you will get. But if the Lagrangian does not have any explicit dependence on time, which means that the partial derivative of the Lagrangian with respect to time would vanish, then the total derivative of this quantity in this bracket will be 0, which means that this itself will be a constant of motion. So, what is a constant of motion? It is this del L by del Q dot, which is P, as we know, the generalized momentum, P Q dot minus L, and this is called as the Hamilton's principal function. So, this is the definition of the Hamilton's principal function, and you can see very quickly, if you take the simple case of the Lagrangian being t minus v for a particle which is moving with a kinetic energy half mv square and a potential energy of v, then you can immediately see that del L by del Q dot and times Q dot will be nothing but this mv square, and then you have to subtract the Lagrangian, which is T minus V. So, this gives you the total energy of the system. So, whenever we think about T and V, we always think of T plus V, which is the total energy of the system, which is fine. But the difference between the kinetic energy and the potential energy is also a physical quantity, T minus V. We think that okay, it is just a mathematical construct. It is much more than that, because from that you can actually obtain the equation of motion for the system. So, it is a very physical quantity. It has got all the information about how the system responds and how the state of the system evolves with time. It tells you the trajectory of the system in phase space. So, it is a very physical quantity, T minus V, and not just T plus V, which is the total energy. So, this is the Hamilton's principal function, and you can extend it to n degrees of freedom. Until now we did not have subscripts because we were dealing with only 1 degree of freedom. But if there are n degrees of freedom, then of course you have to extend this, and there is a similar term contribution from every single coordinate. The Lagrangian is of course the Lagrangian for the total system. So, this becomes your Hamilton's principal function for when you have several degrees of freedom, and you can then ask what will be the differential increment in the Hamilton's principal function, and it will come from increments in qk dot. So, you have from here pk times d qk dot, then it will be because of increment in pk, keeping qk dot constant. So, it is qk dot times dpk, and then you have got minus del L by del qk times dqk. There is a minus sign here which comes here, and then there is again a dependence of the Lagrangian on the velocity, and then the change in the velocity itself. So, this is your general expression for a differential increment in the Hamilton's principal function, and these two are equal because they are, this is nothing but the definition of the generalized momentum. So, this is the generalized momentum with a minus sign, this is the generalized momentum with a plus sign. Both are coefficients of the increment in the generalized velocity. So, these two terms cancel, and you are now left with these two terms. So, del L by del qk is nothing but the time derivative of p from the Lagrange's equation, right. So, let us look at this a little further. So, this is what you get from the previous slide, and then if you write the Hamilton's function, the Hamiltonian as it is called, as a function of p and q, then a differential increment in the Hamiltonian can also be written in terms of the partial derivatives of the Hamiltonian with respect to momentum times the increments in momentum plus the partial derivative of the Hamiltonian with respect to the position and differential increments in the position, right. So, these two relations must obviously be equal for every single degree of freedom. Okay. The coefficients must be exactly equal because the differential increments in the position and moment are completely arbitrary. So, the corresponding coefficients must be respectively equal 1 to 1 for each degree of freedom, and for every degree of freedom k, you can write del h by del p equal to q dot and del h by del q equal to minus p dot. So, notice that there is a change in sign over here, it is coming from here. Okay. So, this sign is important because it ensures that the equations of motion, the classical equations of motion, are symmetric under time reversal. Like Newton's equation, F equal to mass times acceleration. So, acceleration is the second derivative of the position vector, and when you do time reversal, time goes from plus t to minus t. Okay. You have the second derivative of the position in the acceleration, d2r by dt2. So, when you take the second derivative under time reversal, it remains invariant because you are doing it twice. Okay. So, there are two negative changes, and that gives you a +1, which means that the Newton's equation F equal to ma is completely symmetric under time reversal. You can, if from the initial conditions, you can predict where the object will be in the future if you know the initial conditions, but from those very conditions you can also predict where the object would have been in the past. Okay? So, you can do a calculation. If you know the position of the moon today, you can tell where it will be tomorrow, but you can also figure out where it must have been yesterday. So, Newton's equations are symmetric under time reversal, and Hamilton's equations, these are first order time derivatives. Okay? You have got q dot and p dot. So, the time reversal symmetry is not coming because you are taking the second time derivative as you do in Newtonian equation, but here the time reversal symmetry is taken care of because there is a minus sign over here. So, that takes care of the time reversal symmetry. So, both the Newtonian equations and Hamilton's equations and Lagrange's equations also, they are all symmetric under time reversal this thing. So, this is the time reversal symmetry in classical mechanics. In quantum mechanics also there is a time reversal symmetry, but you have to do it carefully because you have to deal with quantum wave functions, and there is complex conjugation of the wave function which is involved. I will comment on this when we discuss quantum mechanical time reversal symmetry at a later stage. So, it is not as straightforward as just substituting t by minus t. You can do that in classical mechanics, but you cannot do that in quantum mechanics. So, I would like to emphasize that this is the principle of stationarity. Okay? It is an extremum, it can be a minimum, it can be a maximum, it can be a saddle point, and there are various properties. Is it a local minimum, is it a global minimum, and so on. So, I will not get into those issues, but this is a very interesting question that you might want to study in further details. And I will like to highlight over here that if you look at action, this is again not just a mathematical construct. It is an extremely important quantity. It results as the definite integral of the Lagrangian between start and finish, between time t1 and t2. Okay? The Lagrangian itself, we realize that it is not just a mathematical construct, it has got physical content. It gives you eventually the equation of motion. The equation of motion is derivable from the Lagrangian. So, it is a very physical quantity, and so is action. As a matter of fact, it is this which is eventually quantized. Means if you look at the dimensions of the action, Lagrangian is t minus v. So, it has got the dimensions of energy, and you are integrating over time. So, action has got the dimensions of energy into time. That is the dimension of angular momentum, and it is this angular momentum which is eventually quantized, and the unit for the quantum of angular momentum, as we all know, is the Planck's constant, or I think it should be called as the Planck-Einstein-Bose constant, because it got its validity only from the subsequent works of Einstein and Bose. So, action is very much a physical quantity, and it is of great importance in classical mechanics as well as quantum mechanics, and we can see its applications in classical mechanics in simple problems. We can look at the famous problem in which Galileo himself discovered periodic motion when he saw a chandelier in a Pisa cathedral oscillating under gravity. He measured the time period by looking at his pulse. Okay? And we know how to solve this, the equation of motion for the oscillator using Newtonian mechanics. So, we will see how it is done using Lagrangian mechanics, and you will see that it is much more powerful, because notice that if you look at the simple pendulum and you set up the equation of motion, so you have got the tension in the string which cancels one component of gravity, okay, and the other component of gravity, which is orthogonal to the previous one, is what provides the force which brings the pendulum back to the equilibrium, and then you write an approximation, the arc length is equal to L theta. Now, this is going to work only when the theta angle is small, not otherwise. Okay? And that is the main point over here, that when theta is small, you can set up this equation in a very straightforward way, which is why you call it as a simple pendulum. It is not all that complicated. It has the same equation of motion as that for any oscillator, be it a mass spring oscillator or in LC circuit or whatever, and you can get the equation of motion. The restoring force is proportional to the displacement and always directed toward the equilibrium point. So, that is, it is as simple as that, and you can solve the equation of motion. But now, if you see, the actual term which is coming in the acceleration is not minus g theta, but it is minus g sin theta. Okay? So, when you consider the term g sin theta, okay, then it is not a very simple pendulum. So, let us play with this relationship a little bit. You can immediately see that the derivative of this term, half of d theta by dt whole square minus g by L cosine theta is equal to 0 by carrying out differentiation of these terms. So, from here you will get half, and then you have twice d theta by dt, and then the second derivative of theta by second derivative of theta with respect to time, and from here you get a sin theta from the derivative of cosine, but then you also have a theta dot, which is d theta by dt, and you can extract the common term d theta by dt from these two terms, and the rest of it is nothing but the equation that you had over here. So, this result is strictly valid. It is easy to see that. So, which means that if the time derivative of what is in this rectangular box goes to 0, then what is this rectangular box itself must be a constant. And you can find what this constant is from the initial conditions. So, if you consider the pendulum, you take it to some angle, you move it and release it with 0 speed. You do not tap it, just let go, so that it comes under gravity. Okay? So, the initial angle at t equal to 0 is, let us say, theta 0, and the initial speed theta dot is 0. So, those are your initial conditions, and if you put those two initial conditions over here, then you immediately see that this speed is 0 and this constant of integration will be nothing but minus g over L cosine of theta 0. So, now you have found what the constant of integration is. So, now look at the solution. It is very interesting. It is something which you may not have seen before. This is what makes a simple pendulum not so simple a pendulum, okay? Because now we are going to take account of the term sin theta. So, here this is your constant of integration. So, you get the speed d theta by dt square in terms of the constant of integration, which is now this minus g over L cosine theta 0, and that gives you the expression for the speed. So, this is the square, so you take the square root, okay? And now you can see that if you integrate this from 0 to theta 0, you get this result which tells you that you do have a periodic motion, okay? However, the period is given by this integral, and this is not a straightforward integral to solve, okay? So, this is not a simple oscillator anymore. We started out thinking that okay, it is a simple pendulum, but this is not a simple equation. You do get periodic motion, but the periodicity expression is not so straightforward. Not only that, the periodicity depends on cosine theta 0. which means that it actually depends on how much you have stretched the pendulum. Whereas in our usual expression 2 pi under root L over G, we never have this angular displacement in the expression for the time period. So, whether you displace it this much or this much, it does not matter, you will get the same time period, which is what makes it so useful as a clock. If the periodic time is going to depend on how much you stretch it, you will have to recalibrate it every time. You can still use it as a clock because motion is periodic, but you will need calibration every time you set the pendulum into oscillations, because it will depend on cosine theta 0. As long as whatever you stretch it by lies within the domain of what you can call as a small oscillation, and the idea of a small oscillation is that it is that angle over which you may regard sine theta and theta to be equal. So, that depends on what level of accuracy you are looking for. Sine theta is an infinite power expansion. You have higher powers of theta, which for small angles become smaller and smaller. So, you can ignore it, but do you want to ignore it after the 5th term or the 10th term or after the 50th term? That is a choice that you can always make, and depending on that choice, depending on where you truncate that infinite series, you can have the approximation sine theta equal to theta if you decide to truncate it at the very first term, not otherwise. Okay. So, in general, this is not a simple pendulum, it is periodic, but you will have to recalibrate it every time you shift it. Okay. So, for small angles sine theta equal to theta works, and you get a periodic time which is independent of theta 0, but not otherwise. Okay. So, now let us look at this integral. How do we evaluate this time period? Now, we do not want to throw off the subsequent terms. If you do not want to do that, then you really have very complicated expressions. So, let us see what form they take. So, you have got, we will use some trigonometric identities. So, you have got an expression for cosine theta in terms of half angle. You will have a similar expression for theta 0, which is the initial angular displacement. You can take the difference which is coming under the square root sign in the denominator here. Okay? And then you can write this expression in terms of these half angles. Okay? So, now you see that it is a complicated integral, and you can solve it by carrying out some transformations. It is useful to change the variable from theta 0 and theta to xi and u, and these we introduce xi as the sine of the half angle theta 0 and u as sine inverse of this ratio sine theta by 2 divided by sine theta 0 by 2. So, theta 0 is the initial angular displacement. So, in terms of the initial angular displacement, you introduce these two variables, so that instead of theta and theta 0, we will use the variable xi and u, and then we will transfer the integration over theta to integration over u, over the variable u through this. So, you have this result which you use to transfer the integral over theta 0 to integration over u. So, this is how it is done, because you find you differentiate both sides of this relationship between xi and theta, and then you can rewrite this integral in terms of the variables u and xi. So, there is no new physics in it. It is the same integral, except that we have now written it in terms of xi and u instead of theta 0 and theta. So, rest of it is, you know, elementary algebra, transforming the variable from theta 0 theta to xi and u. So, this is now your expression, and you have got this square root term in the denominator. So, you can expand this. Okay, you can expand this, and what you have are complicated integrals which are called as elliptic integrals of the first kind. And yes, you can certainly solve this integral. you can get an expression for this. So, you can expand this in powers of xi square and put in this expansion over here. Okay. So, once you do that, carry out some systematic algebraic transformations which are not very difficult. I leave them as exercises for you to work out. You do get an expression for the time period. It is periodic, the motion is periodic, but it depends on the initial angular displacement theta 0. So, unlike the simple pendulum whose periodic time is independent of the angular displacement, the not so simple a pendulum, which is a simple pendulum for which you do not approximate sin theta equal to theta, has a periodicity which depends on the angular displacement, and it is a very complicated expression, as you can see. Okay, it has come from that power series expansion. So, this you can subsequently expand sin theta in terms of theta. So, sin theta 0 in terms of theta 0 itself and get an expression in terms of theta 0. Okay. So, you get a power series, you get expressions in power series of theta 0 square, and there are all kinds of coefficients, 173 over 7372880, which is the coefficient of theta 0 to the power of 6 and so on. And you will have to do this kind of calibration every time you have a different displacement, you set it into oscillations. So, how do you get around it? You want to have a pendulum whose time period will not depend on this. So, you have a complicated expression, and Huygens, he was a brilliant inventor, and he was also a clock maker. He used to construct different pendulum clocks, and he figured that okay, the reason this sin theta equal to theta approximation works is because this motion is on the arc of a circle. Okay, that is when you can make this approximation sin theta equal to theta, and this is a necessary reason which will make the time period independent of the displacement. If you want a pendulum which will give you periodic time which is independent of the displacement, then it must move on the arc of a circle, because if it does not move on the arc of a circle, then the approximation sin theta nearly equal to theta cannot be made. So, Huygens' conclusion was brilliant. Suppose it does not move on the arc of a circle, it moves on some other shape. It is not an arc of a circle. Then there is a possibility that you can come up with a pendulum which will not depend on how much the angular displacement is. So, you have to construct a pendulum such that it will not move on the arc of a circle, some other shape. Okay? And he figured out what that shape must be like, that the trajectory must not be the arc of an exact circle, it should be some other shape, not a circular shape. All right? So, how do you do that? You do that by inserting what are called as chops. So, you have got the pendulum is suspended from this, and you do not let it go freely. As it comes here, you obstruct its motion by having some obstruction over here. When it starts moving in this way, you have some sort of obstruction over here. So, these are called as chops, and these chops used to be made of either wood or brass and so on, and clockmakers knew how to use them because they were using it to design their clocks. So, Huygens came up with using chops. These are stoppers made of brass or wood, and what it does, it shapes the trajectory on which the bob moves. Okay? So, by in introducing appropriate chops, and there is a very nice video on the internet which was being developed by Professor Tatum, and I will use it. The reference is given here in the lower left of the slide, and what this chop does, as you can see, okay, it stops the pendulum from moving freely. It obstructs its motion on both sides, okay. And notice that the angular displacement, there are different colors of the pendulum. These are different pendula. There is a purple, there is a blue, there is a green, there is a yellow, and there is a red. And they all have maximum displacements which are quite different from each other. The maximum displacement of the red pendulum is rather small, but the maximum displacement of the purple pendulum is quite large. Okay? But do you notice that they all have exactly the same periodic time? They have different angular displacements. That of the red pendulum is very small displacement, but that of the yellow is more, the green even more, the blue even more so, and the purple the largest. And no matter how large a displacement it is, the periodic time is exactly the same, and this has been achieved by inserting these chops and by shaping the chops along a particular curve. Okay? And this curve is familiar to you because you have seen it in the Brachistochrone problem. This is the cycloid. Okay? So, this is the cycloid, and this is not an easy problem to solve using Newtonian mechanics. And the reason for discussing it in today's class is to demonstrate how easy it is to work with Lagrangian formulation. What are the chops doing? What are the stoppers doing? They are constraints. Okay? And the forces of constraints are so complicated to be included in the Newton's equation of motion. But in the variational principle, in the Lagrange's equation, you are not bothered about the constraints because your equation of motion does not even have them. Your equation of motion gets rid of the constraints. It formulates the equations of motion in terms of those degrees of freedom which are independent of constraints. So, you reduce the problem from your usual Cartesian or any coordinate system and bring it down to the essential degrees of freedom, which are the independent degrees of freedom. Set up your Lagrangian, and then you see what is the equation of motion. So, it turns out to be a very easy thing to do because you can set up the Lagrangian as T minus V, okay, and then the kinetic energy is half m x dot square plus y dot square and mgy in Cartesian, but we can set this up in terms of the independent degree of freedom, which is theta, which will be the solution to a cycloid. Okay? So, let us see how it comes. So, you have got this cycloid trajectory. We have discussed this in the context of the Brachistochrone problem in the previous class. So, I will refer you to the previous class to remind yourself of the equation to the cycloid, which I am not going to derive again. We have already done it in the previous class. And if you see that this is the trajectory of the bob and x, y are the coordinates of this. So, what is x? X is st from here to here minus p to q. Okay? This is the x coordinate, and likewise y is ct minus cq. But what is st? St is the same as the arc tp, which is this arc. That is how the circle is rolling, starting out from the initial point, which is the start. So, it is very simple geometry which gives you the equation to the cycloid, and you can write this equation, the Lagrangian, in terms of the r and theta instead of x and y. So, when you do that, you carry out these transformations because x is related to r and theta from this relation, and y is related to r and theta from this relation, because x is nothing but st minus pq and y is nothing but ct minus cq. So, that is a simple geometry which you make use of, and write the Lagrangian in terms of this, and now you can solve the Lagrange's equation. Okay. So, this is your Lagrangian. So, you get the to get the Lagrange's equation, you need the partial derivatives with respect to velocity and with respect to position. You need the time derivative of the partial derivative of the Lagrangian with respect to the velocity, which is the generalized momentum, right. So, you take the partial the time derivative of the Lagrangian of the generalized momentum, and now you can write the Lagrange's equation. So, you got theta double dot, you can put this in the Lagrange's equation and get the relationship between theta double dot and theta. So, what is that relation? So, now you have not thrown off the sine theta term or anything like that, no such approximation is involved. This is this is coming from the cycloid, right. And if you see this, all right. So, let us take this last step to the top of the next slide, okay, and simplify this for theta double dot. So, everything else moves to the right hand side, okay. So, there is no big mathematics done over here except rearrangement of terms, and you recognize the fact that you can take the time derivative of cosine theta by 2 and take the second time derivative as well, substitute it in the original expression, and now you get a very fascinating result. What have we done? We have written the equations in terms of the Lagranges. Okay, so, we construct the Lagrangian in which we are choosing that cycloid trajectory. We write it in terms of the generalized coordinate, which is theta. Okay? And in terms of this theta, we have written the Lagrangian. Now, we write the Lagrange's equation, okay? And then we have simply carried out some straightforward algebraic transformations. Okay? There is nothing beyond high school algebra in this and geometry. So, you have this expression for the second derivative of cosine theta over 2, and notice that the acceleration, the left hand side is the second derivative of this argument. Whatever that argument is, it is the second derivative, it is the second time derivative. That is what acceleration is, right. Acceleration is the second time derivative of a certain function. This function over here happens to be cosine theta by 2, and this second derivative is equal to minus g over 4r times the same function, which is cosine theta by 2. Now, this is just the equation for a mass spring oscillator or the expression for a simple pendulum. This makes it similar to the simple harmonic oscillator. We started out with a not so simple harmonic oscillator, but we have a result which is like a simple harmonic oscillator. Why do we get it? Because of the use of these chops, okay? But the time period is different, it is not the same as the simple harmonic oscillator. So, now you have got this acceleration given which is proportional to the displacement. It has got a negative sign, which means that it is always directed toward the equilibrium point, and this is just the expression. So, now for this we can get the periodic time. So, it is not 2 pi under root L over G, it is 4 pi under root R over G, where R is that radius of the circle which exercises that cycloid motion. So, this is really amazing. And now, look at this expression, it is so beautiful. It does not have theta 0 in the periodic time. This was our worry, that for larger displacements it will work, it does not care how large a displacement is, okay? which is why even though the displacement of the purple oscillator is so huge, the displacement, angular displacement for the yellow pendulum is larger than that for the red, that for the green is larger still, for the blue pendulum it is even more, and for the purple it is the most. So, they all have angular displacements which are progressively larger and quite huge. Obviously, sin theta equal to theta will not work, okay? But not a problem. You still have a periodic time which is independent of how large the pendulum is, and you are able to see that result in such a simple way using Lagrangian mechanics. But just imagine what it would take to do it using Newton's methods. Newtonian mechanics will require you will get the same result, but you will have to take into account these constraints, and these constraints are determined by normal reactions and so on, and this is over a very complicated trajectory. Okay? So, it will be very difficult to do this problem using Newtonian methods. So, the chops also have the shape of a cycloid. So, these are half cycloids actually on each side. So, these are semi-cycloids, and what they are doing is that they change the effective point of suspension. The effective point of suspension, which is right here under the tip of this arrow, all right, but now it slides along the surface of the chop. The point of suspension is effectively sliding along the surface. So, you can shape it appropriately, and you are sliding it along the surface of cycloid or two semi-cycloid, because what happens is, and this is a matter of detailed geometry, the involute of a cycloid is also a cycloid which is completely congruent to the original cycloid, except that it is displayed. So, the motion of the bob is along this cycloid, okay, but the point of suspension is along two semi-cycloids. So, they are all cycloids given by the same equation. The equation of the cycloid is exactly the same for all the three. The left chop, the right chop, and the cycloid along which the bob itself is moving, they are all given by the same one, except that the cycloid along which the bob moves is displaced. Okay? So, there are three different cycloids which are displaced from each other, but they are all given by the same equation, because the involute of a cycloid is also a cycloid which is congruent to the original cycloid. So, these are some geometry theorems which I will not get into, but I have used this example to demonstrate the power of the Lagrangian mechanics, that a problem which is otherwise so complicated, we find that the simple pendulum is really not so simple. You do get periodic motion when the displacement is more, but then that periodic motion depends every time on how much angular displacement you have used, so to set it into motion. So, every time you will have to calibrate it, and then to determine that periodic time you will have to solve all those elliptic integrals and so on. So, it is a very complicated system, but on the other hand you can get a pendulum even for large oscillations without having to bother about calibrating it every time, by making the point of suspension slide, okay, smoothly, beautifully slide along these chops, along these wooden or brass stoppers, all right, and by using them you get a periodic time which is independent of how far the bob will be moved. It could be the red bob which is moved just a little bit, or the yellow or the green or the blue or the purple which are moved much more, and you get exactly the same periodic time. So, the time that each of these colored pendulum or pendula take to complete one full oscillation is exactly the same, irrespective of how far it is displaced. So, this is a beautiful example of the power of the Lagrangian, and in the next class I will discuss the variational principle and some other applications to demonstrate its power. But today's class we conclude here. If there is any question I can take, otherwise we will continue from this point next.
So we have the Hamiltonian,
Yes.
that is a sum of kinetic energy and potential energy. Will it be like that in every case? Total energy would be equal to Hamiltonian?
If all the degrees of freedom are taken care of, it will be the same. If some degrees of freedom are not taken care of, like friction, okay, you are writing the Hamiltonian for this object and the motion involves, you know, moving it along this table from here to here, okay. Then there are degrees of freedom of the table. It is interacting with the particles of the table and it can exchange energy with that. And you are not taking that into account when you write the equation of motion for this object. Okay. So, all the degrees of freedom are not taken care of. There are these what I like to call as unspecified degrees of freedom. And whenever you have these unspecified degrees of freedom, you are not keeping track of the energy exchange at a microscopic level. Okay? And then the energy of this system cannot be constant. That is what we mean by saying that friction is dissipative. The reason energy is lost in friction is because you have not kept track of the energy exchanges with other unspecified degrees of freedom. Same in viscosity, or same in if the pendulum is interacting with air or it loses energy at the suspension where it is rubbing with something with which it is held at the top. So, whenever you take into account the unspecified degrees of freedom, energy cannot be constant, energy is lost. Okay? Otherwise, fundamental interactions in nature, I mean the fundamental interactions over here which we are concerned with are only gravity and electromagnetic, right. The energy exchange with this will be essentially electromagnetic and gravitational. Of course, at a deeper level you also have to bring in quantum theory, but if we do not get into those details, even the electromagnetic interaction is fundamentally conservative. So, no energy can really be lost. So, when we say that energy is lost, it is not that okay, it is really lost. If energy can be lost by friction, you can just rub your hands long enough and destroy the whole universe, right? Because energy is getting lost. So if we just do that, we can destroy the universe. It cannot get destroyed like that. Okay? Energy goes into something else. It can even heat the two objects and can get radiated out. Okay? So, there are many modes in which energy can be redistributed without really getting lost. So, the term lost is not a very accurate one. It is lost to the mathematics of the equation of motion, not lost in nature, it just goes somewhere else. So, if all the degrees of freedom are taken into account, then the Hamiltonian will be a constant of motion. Okay, thank you.